Alright, this is the last of the 3 videos revisiting the skills needed for success on our unit in kinetics and equilibrium. Alright, I decided to try to mess you up and move my picture over. Number 16. Given the equation representing a reaction at equilibrium, we have nitrogen gas, 1 mole of it, combining with 3 moles of H2 gas in equilibrium with 2 moles of ammonia gas. So what occurs when the concentration of H2 gas is increased? So Le Chatelier said that as you increase the stress, the system is going to behave to relieve that stress and move away from it. So we are increasing H2 gas. The system will then shift to the right. In doing so, because we added more hydrogen gas, there is now more hydrogen gas to react with the amount of nitrogen that has been the same. So as we shift to the right, it's going to drag more nitrogen with it to help produce more ammonia. Which statement states that? So it says the equilibrium will shift to the left. The equilibrium will shift to the left. Equilibrium will shift to the right, liking it. And the concentration of nitrogen decreases. Loving it. But let's just confirm. Number 4, the equilibrium shifts to the right, liking it. And the concentration of N2 gas increases. I love 3. I hope you do too. Alright, number 17. Given the equation representing a system at equilibrium, here we have, once again, 1 mole of nitrogen gas, 3 moles of hydrogen gas, in equilibrium with 2 moles of ammonia gas. This time energy is being identified, unlike the last question, and because energy is on the right side, it suggests that energy is being released. We need to identify that is now separate. It is going away. It's exothermic. So which changes occur when the temperature of the system is decreased? I don't like answering the question like that. It's harder for me. I like to pretend that the energy was increasing. Because I know if the energy increases, everything shifts to the left, decreasing ammonia, increasing my hydrogen gas, and increasing my nitrogen gas. But I'm not increasing it, I am decreasing it. So therefore, everything must go in reverse. We are shifting to the right. So which one of these choices matches? The concentration of H2 increases? No, we're shifting to the right. The concentration of H2 decreases? Looking good. And the concentration of N2 gas increases? No, if it's shifting to the right, it all decreases. All right. The concentration of H2 gas decreases? Looking good. And the concentration of ammonia decreases? No, if it's shifting to the right, the ammonia must increase. Or the concentration of hydrogen gas decreases, looking good, and the concentration of ammonia gas increases. Love this one. But I got a follow-up question. What if the pressure was increased? Well, similar to questions before, we would add up the total moles of gas on the left, and that's 4 moles of gases on the left in equilibrium with 2 moles of gases on the right. If we increase the pressure, we will therefore be shifting, grab my pen, shifting the reaction to the right. That would then decrease the nitrogen, decrease the hydrogen, and increase our ammonia. 18. Which equation represents a change that results in an increase in disorder? Increase in disorder is our term entropy. Alright, now which one is becoming less orderly, more scattered? Is it when you go from a solid to a gas to a solid? We got solid gas to a solid, so gas to solid, or gas to a liquid. Well, only one of these is actually going in this direction. From the solid, which is very orderly and organized, to a gas. And that choice is choice number 1. Alright, we now need to base our answers for 19 and 20 on this information. We have a situation where at 550 degrees Celsius, that's hot, 1 mole of carbon dioxide gas and 1 mole of hydrogen gas are placed in a 1 liter reaction vessel. The substances react to form carbon monoxide gas and water vapor. Changes in the concentrations of the reactants and the concentrations of the products are shown in the graph below. So we have time moving on from T0, when the stopwatch would be hit for the first time, to T1 and T2. We have concentrations in moles per liter, so that's the number of solutes per liter solution. And we do have values. Here we have our reactants. Okay, reactants very high here at the very beginning, and those reactants are carbon dioxide and hydrogen gas. And products, at the beginning there are no products. It's the beginning. So the products are changing as time moves on, producing carbon monoxide gas and water vapor. The question: what can be concluded from the graph about the concentrations of the reactants and the concentration of the products between time T1 and T2? So from here to here, the concentrations. Again, this is concentration. Between these two regions, what is happening to the concentration level? No change in concentration. Those brackets imply concentration. So let's make sure that I answered the question. What can be concluded from the graph about the concentrations of the reactants and the concentrations of the products between times T1 and T2? Are they changing? There's no change. Now here is our second question for the same diagram. It is: determine the change in concentration of carbon dioxide gas between times T1 and T0. Actually, T0 and T1. So here is T0, here is T1, talking about carbon dioxide. So what is the change in concentration? We go from right here. Ooh, let me undo that. Okay, right here to, well, and right there. So it's actually starting right here, going to there, and determine the change. What is that change? Well, 1.00 minus 0.73. The change in concentration is 0.27 moles per liter. Okay, now here's another consideration. When a system is in equilibrium, all of the qualities and quantities of the substances on both sides of the equation remain constant. For instance, concentration and change in energy remains constant. If we're talking about phase equilibrium, the amount of the substance becoming a gas equals that of what becomes the liquid. So the concentrations remain constant. Keep that in mind. Now here's another question. If this were water, at what temperature would liquid and solid be at equilibrium? Now I failed to mention that we have to say at constant pressure. So at constant pressure. Now that is important because we do know that substances boil and freeze at different altitudes. Remember our unit on solutions when we talk about vapor pressure and how boiling point and freezing point get affected with altitude. Mostly boiling point we talked about. But the same also is true for freezing point. So again, if this were water, at what temperature would liquid and solid be at equilibrium if we're at constant pressure? Now, to do this, we would identify the point in which solid, let me grab a nice pen, solid and liquid are being converted into each other, so we're at equilibrium here. And what is this temperature where water becomes a solid and liquid water becomes a solid and solid water becomes a liquid? And we know that to be 0 degrees Celsius. And now for our last slide. I would like to walk you through the thinking map we produced in class related to Le Chatelier's principle, where it talks about how the stresses impact chemical reactions. And let's go down this branch here. And this branch talks about if you increase the concentration of reactants. Reactants, as we know, well, let's just say A plus B is in equilibrium with C plus D. And let's put energy here. Just energy. All right. Now let's also assume that we have 2 moles of this, 5 moles of this, and everything is a gas, so we could have this conversation. All right. So what happens if we increase the concentration of the reactants? Reactants are right in here. Well, the system will shift to the right. Now, this will then decrease the concentration of the other reactant. Okay? And it will increase the concentration of the product because it is going to the right. Now, let me undo this so we could look at all the writing in the next branch. Now that gives us enough room. On this branch, we increase the concentration of the products. Well, if increasing the concentration of the reactants shifted it to the right, then increasing the concentration of the products must do the opposite, shifting it to the left. And what that will also do is decrease the concentration of the other products, if they are at all available. And it will also increase the concentration of the reactants. All right. Now, next branch. If we increase the temperature, well, if it is an exothermic reaction, which the one I depicted on top is, we're adding more energy on the right side. That's where the stress is. Everything shifts, in this case, to the left. And last but not least, increasing the pressure. That relates to if there's a gas. Now, that affects the reactions that have only gaseous substances because it increases their concentration. Now, it's not saying that everything happens to be a gas. There could be solids in there too, but the concentration of the gases will increase. And if it's on the reactant side, push it to the right. If it's on the product side, push it to the left. So it shifts the reaction away from the side with the greater number, total number of term here relating to concentration is, where's my pen? Moles. Now, we could also talk about, instead of increasing concentration, decreasing concentration. Obviously, it would be opposite. Decreasing concentration of the products would be opposite. Decreasing the temperature would be opposite of this. And decreasing pressure would be the opposite of this. Still be the moles, but it would go in the opposite direction. Now, Tricia, what do you got to say?
Good luck!
Good luck.